All right, thanks, Paige. Yeah, it's just super fun and exciting to be here. For context, Joe and I helped get Pangeo off the ground about 6 years ago, and it's been amazing to see the community grow over the years. And about a year ago, Joe and I did this crazy thing of quitting our jobs and going off to start this startup called EarthMover. And we've been kind of, pretty quiet until recently, and we're really excited to share with everyone here what we've been up to. And what we've been up to is building the cloud platform for scientific data teams. I'm going to tell you all about it. But first, I want to tell you a little bit about our team. So EarthMover is a startup, and we're a public benefit corporation, which means we're a for-profit company, but that has a mission to benefit the public written into our charter. And our mission is to empower people to use scientific data to solve humanity's greatest challenges. So, the way we're tackling this mission is by building a unique team that brings together folks like myself and Joe, who are experienced scientists, open source developers, who really understand what practitioners are trying to accomplish in terms of research and building systems that work with data. And we joined forces with some amazing seasoned engineers who've been building production-grade scientific data infrastructure at top companies like Google, AWS, Planet, and Climate. And by bringing these types of people together, we really think we're in a unique position to be building the scientific data platform of the future. Next slide, Joe. So I think we probably don't need this introduction for this crowd, but it's always important to me to start by just really confronting the complexity and the beauty and the challenge of Earth system data, right? So this video from NASA gets it across really well. There's so much data about our planet today, and these data have the potential to really help us as a species adapt to and mitigate climate change. We can use the data effectively. But there's also massive flood of data. The complexity, the velocity, and the size of this data makes it really hard to work with. And these are the challenges that folks here in the Pangeo community have been confronting head on for many years, right? And so we're fortunate that there's a common data model behind so much of our Earth system data, right? And Joe and I have gotten our perspective on this data model by working together on the Xarray Python library for many years. So Xarray kind of encodes this data model that underlie just about all of our system data, which is a structured scientific data model, multi-dimensional arrays with metadata, maybe the NetCDF data model, CF conventions, all of this stuff, right? We actually have this wonderful universal data model that underlies so much of our data. So all of those fields on that beach ball video in the previous slide can be represented with this data model. And it's been great to see how Xarray as a tool has grown in adoption, is now used across the board on so many different interesting and important scientific problems. But I don't think we're done. There's still a lot of challenges that folks have to confront when building scientific data systems, right? So to illustrate what these are, the typical use case we like to think about is a team at an insurance company who has been tasked with the goal of understanding how the insurance company's exposure to wildfire risk will change over the coming decades, right? So this is a really interesting, really important, and really data-intensive problem. And on this slide, you can sort of see what are some of the typical steps involved in a workflow like this. And maybe you recognize some of these steps from your own work. And the question we want to ask, is where should a team like this be storing all of the data that go into a scientific data pipeline? It's probably going to be hundreds of terabytes of data for typical applications. Well, they're going to need some sort of data lake where that data is accessible to their team and operational. But how should that actually be built, right? And so on the next slide, we'll take a look at, what are the options available to folks today, right? So when you're going to store hundreds of terabytes of multidimensional array data in the cloud, you basically have two high-level options. Now, one of these options is to use a managed service like a data lakehouse or data warehouse platform. These aren't that widely known and widely used within the Pangeo community, but they're absolutely ubiquitous in more sort of traditional data science and business data analytics applications. So this is something like Snowflake, Google BigQuery, or Databricks. And so these types of solutions are really convenient and attractive to organizations because they're just a turnkey out-of-the-box solution that doesn't have anything that has to be built or custom designed. They have a really good story around data governance, data versioning, transactions, data catalogs, access controls, and they have powerful integrated computing layers that make it really easy to operationalize your data. Of course, the reason no one in this community really uses those things is that they don't really understand array data. They don't understand what's in a NetCDF file. They're really based around the tabular data model. If you want to try and squeeze multidimensional array Earth system data into one of those solutions, there's a lot of pretty unacceptable trade-offs that have to be made. So instead, what we see people doing is building their data lake on top of cloud object storage, things like AWS S3 or Google Cloud Storage. And this is so ubiquitous in our community, we almost take it for granted that this is what it means to store data in the cloud, right? Now, this is really attractive because we get to keep the array data model. We get great integration with data scientists' preferred tools, things like Xarray and Zarr, and we can get really good performance if we know how to tune those tools well. The downside here, of course, is that there's a lot of custom engineering required to build a really production-grade data lake using this approach, because so many things just don't come out of the box when you're building with S3, right? So there's the data governance story is pretty complex. How you do data catalogs is a big problem. And there's no real integrated compute solution that integrates tightly with this approach. And so, we see folks being successful here, and we see them mostly using the Pangeo tools that this community has helped develop. Joe, I think there's another slide that will show what I mean there, right? So using tools like Xarray and Zarr can help you build the foundations for a data lake, but there's still a lot of custom engineering required. And that need for custom engineering is holding back teams that are trying to build products to operationalize climate adaptation and mitigation. It's also holding back, I think, academic institutions from adopting this approach, because a lot of academic institutions like university labs don't really have cloud DevOps engineers to build those custom layers. And so just throwing them object storage and saying, go, this is what you have to work with, isn't a full solution to their needs. So this is the problem we're trying to solve with Arraylake. So Arraylake is a turnkey data lake platform for scientific data. And our goal is to give developers a 10x better experience than just dumping their data into object storage. And so that includes a high-performance cloud-native API for reading and writing multidimensional array data, which is fundamentally the Zarr API. A user-friendly data catalog that is always and automatically in sync with the contents of the data lake. Some sophisticated database-style functionality, such as atomic transactions and data versioning for the Zarr data model, which are really key to reliable production-grade systems. And finally, a virtual file approach that allows users to ingest both Zarr, but also HDF5, NetCDF, Tiff, and Grib really trivially without having to really worry about the underlying file format. So how does Arraylake work? Well, you can think of it as a meta store for the Zarr data model. So the sort of standard architecture that's widely used today in our community is shown here on the left. And in this architecture, the metadata are stored in the object store itself in JSON files. And that's not actually a great way to store a bunch of metadata. It's not very useful in that state. So with Arraylake, we route the data into two different locations. We're still storing chunk data, the big data, in object storage, but all of the metadata are stored in the Arraylake backend service. That allows us to make the metadata searchable. That allows us to create a data catalog that's always in sync with the data. And this metastore, in essence, is the data catalog. And it makes it really easy to do things like implement moving, renaming, transactions, version control, and provides this indirection layer between the chunks in object storage and the actual objects that are stored. One more slide, and then we're going to switch over to the demo. So what we've built today, is a product we've been working on for the past year, and we're really excited to share it with the world. And at the end, we'll tell you about the private beta program that we're launching. But I also want to mention it's really only the foundation for a much more full stack solution. So now that we have this data lake foundation, we're excited to start building elements around data sharing, compute engine, and integration with AI ML pipelines, which are the things that we see all of our customers actually using this data for. So I think I'll stop there and I'll turn it over to Joe, who is going to give you guys a demo of Arraylake.
Great. Is everyone seeing a Jupyter Lab screen now?
Yes. Yep. Good.
Someone is? Great. Okay, cool. Well, first off, it's great to be here, and it's great to be sharing Arraylake with all of you today. So what I'm going to do is I'm going to walk through a Jupyter notebook, and I'm going to kind of highlight 4 of Arraylake's main features. So Ryan just gave a really good introduction into what Arraylake is and architecturally how it works. But now we're going to jump into some Python and take a look at how you might use it in some sample applications. So first thing we're going to do is look at Arraylake's data catalog functionality. So as we've discussed, like S3 itself provides a pretty poor interface as a data catalog. It's really best thought of as an undifferentiated key value store. And almost everybody eventually needs a catalog about their data in S3. People use text files or spreadsheets or even other databases to do that. And I'm going to guess that everyone here, if you've used data on S3, has done something like this. Maybe you've done this on a file system on your supercomputer. But you've LS'd a directory, and then you said, oh, okay, now I know what's in that directory, so let's choose a subdirectory. And then, okay, yeah, now I've drilled down. Eventually, I'm going to find some Zarr datasets here. And now that I've found those Zarr datasets, I can use the file path essentially to decide what's in them, but I still don't know what's actually in the Zarr store. So, this is about as much as you can get out of S3 itself. And then now let's talk about how it works with Arraylake. So, as Ryan said, the Arraylake service has its own database that maintains the state of each store, and we call these repositories. So the general hierarchy, the data model in Arraylake is that you have an organization. Call it, EarthMover is our organization. You can have a collection of repositories. You can think of those as like Git style repositories. They're all their own versioned Zarr hierarchy, but they're independent versioning. And inside of each hierarchy, you can have groups and arrays. And obviously within the arrays, you have chunks. And so that's the general data model. And what we're going to do next is we're going to import our Python client. So the Arraylake client, we're going to instantiate it. And we're going to check out our repository. Actually, this should have a repo.checkout. Last minute change to that cell, and we were about to hit an error. So what we've done is we've gone and fetched the repository and checked it out, and now we're ready to work with it. So the first step, what we're going to do is we're going to ingest some data into Arraylake. So here we're pointing at the Era 5 public dataset program, and the version of Era 5 in Amazon's public dataset program. And we're just grabbing 2 variables for 1 month in 2023, so it's January 2023. And we're just looping over those variables, opening them with Xarray, rechunking them, and then writing them back to Zarr. And we're using Xarrays to Zarr method, and this repo.store is where Arraylake comes in. So that repo object exposes this store attribute, which is a valid Zarr store, and we can do Zarr things with it, including pass it to X-ray and let it write data there. So while I was talking, we ingested these two variables for 1 month, and we can take a look at the tree view of this repository now, and we see, yes, we have 2 groups, each with 4 arrays in them. And remember that we have 744 time points. We're going to come back to that in a little bit when we extend this data set. So that data is in a staging area right now, but it doesn't become visible to any of my teammates, say, until after I've committed it. And so I'll commit it. And at this point, this data is going to be visible to all of my teammates, and including anyone that can access the our web app. So I've been showing the Python client so far, but one of the benefits of putting this data, your data in Arraylake, is that we also have the data catalog visible through a web application. So here I'm now looking at my Zarr store in the metadata of this group, and its arrays here. I can actually click on one of these arrays and immediately see details about my array, everything including the Zarr array storage schema. So I can see its chunk shape and its dimensions and that sort of thing. And I can see the user attributes. And as I'll show later, we'll be able to take advantage of the fact that Arraylake understands all these later on. So fully integrated data catalog, both the Zarr store all the way through all your data catalog features are right here. We can, of course, just turn around and open this data set again with X-ray. And so here I've just pointed at one of the groups, and I've opened this up, and I'm able to quickly make a plot of this. So standard X-ray stuff here after opening the repository with X-ray. The next thing I'll show is how transactions and commits work. So we've already done one commit, but we'll do some more here. Let's go ahead and, well, let's first talk about what transactions are. So because Zarr datasets span many files or objects, it's very easy when you have multiple readers and writers working on that dataset at the same time for one writer to update, say, the array metadata, and then another reader come along and see an inconsistent state while the dataset is being updated. And this really breaks production systems, and it also leads to confusion about what the state of your Zarr store is. So with Arraylake, we implement transactions, which allow you to stage changes and then atomically update your store all at once. So here, what we've done is we've opened up another month of Era 5, and we're going to append that to one of the groups. So you see here, we're saying dataset to Zarr, passing that repo.store object again, and over here we're appending along the time 0 dimension. So we can create a quick plot. Here you see we're also using Dask to do this, this computing. And you'll see there's 2 months of data here. So we have got both January and February of 2023. And you see there's now 1,416 time points in this variable. So we have indeed grown the size of this array. So let's now simulate what it would be like to view this repo from another reader. So here we're going to create a new repo object. We're going to call it repo2. This is like if one of you had connected to this repo. We're going to check it out, and we're going to look at the time array, and we're going to see, oh, it's only 744. And the reason for that is I haven't committed those changes yet. And so if I do commit those changes, now I've just made a commit. I'll just repeat this step by checking out the repo2 again. So this is going to refresh the commit history. And you'll see that now all at once I get the visibility of this new array. So so that's how and of course the web application is going to see these changes as soon as I've made that commit. So we'll be able to see that the time dimension here is 1416. Okay, let's talk about a little bit more about versions and immutability and time travel. So one of the problems we've seen a lot of teams run into is they want to incrementally change their Zarr store over time, but they want to be able to reference the state of their Zarr store at a given snapshot. And so without Arraylake, you just have to create a new copy of the data set. And I've been on projects where we've created many copies of the exact same store, but with minor alterations, and that's really inefficient. And it also means you have to build a lot of engineering to track those over time. So with Arraylake, we can utilize this the versioning to allow for time travel, and so that's what we're going to show here. So right now we have 2 commits. We wrote some data and then we extended that. You see we have 2. You can actually just look at the commit IDs, and we'll go ahead and look at the length. We can skip the tree cell and just look at the length of these 2 time variables. So here's commit 1. See the time length was 744, and then we can look at the later commit and we can see that it's 1416. So not only can we atomically update the state of our repository through transactions, but we can also roll back changes to a previous state. And you can see these warnings are just telling me you're no longer on a branch tip. This is a detached head state equivalent if you were using Git. It's just saying you're not you're in an immutable part of the version history. You're not going to be able to make changes here. Those are expected warnings. Okay, well, finally, let's look at how we handle virtual files. So we've got petabytes of data stored in archival formats, a lot of which is either in the cloud today or moving to the cloud. And we want to be able to interact with that data in a cloud native way. And so there's really a few ways you can do this. The old way, we'll call it the old way. Option 1 would be to just download the file to our local machine. So I'm running this Jupyter Lab session in the cloud, so I can download this data. Here's a NetCDF file. I'm downloading it right now. Once it's done downloading, that's what this step is doing, I will be able to open that. So it took 19 seconds to download that data set and then open it up with X-Ray using NetCDF. Of course, I think many folks on this call will be familiar with Kerchunk. So here's an example of how you would do the same thing with Kerchunk. So we're going to use S3FS. We're going to open that file handle. We're going to connect to, or we're going to scan that file for its virtual references, and we're going to output this JSON file. And we can, with some magic from FSSpec and the reference file system in X-Ray, we can open that that data set. And that was faster. It also didn't require us downloading the whole file, and it worked great. The challenge there is now we have this kerchunk.json file. This is essentially a sidecar that we have to carry around with the NetCDF file as well. And so, and then the final example here I'm going to show is with Arraylake. So how would you do this with Arraylake? And Arraylake offers this add virtual NetCDF method, which is similar to Kerchunk. In the case of NetCDF, it actually uses Kerchunk behind, under the hood. But rather than storing those references in an external file, we can actually put those references in our backend database. And that means we can take advantage of all the other Arraylake features like versioning and catalog and all that with, I should have run this while I was talking, but we can take advantage of all of Arraylake's features while we're using these virtual files as well. So here I went ahead and I ran this add virtual NetCDF, went ahead and added that commit. We can immediately open that up with X-Ray, do X-Ray things like make a plot with it. We can also open that up in the web app and immediately see the NetCDF file, the contents of the NetCDF file, but now in the Arraylake platform. Two more quick bonus features to talk about. The first is metadata search. So we've talked about how having all of that Arraylake is a metastore, and it allows us to use stat metadata in more interesting ways. And so here's an example of how we could search on across that metadata. So I'll walk through what these steps are doing. First off, this is an experimental thing, so that's why you're seeing the warning here. But here we're going to point at a new repository called the Pangeo Forge repository. It's just a virtual mapping of all the data sets in Pangeo Forge today. And it's a nice demo because I can search across all the feed stocks in Pangeo Forge for data sets that match this one tag or this description, DAMIP, hist error. So went ahead and ran that and I found, oh, there's only one group with that. That's great. So let's go ahead and open up that that group. And in just a couple seconds, I've searched across a bunch of data sets, found my group, opened it up, and gotten to work. So that's an example there. We could open this up with the web app and take a look at that page as well. And then finally, I'll just point out that I've showed off the web app in the Python SDK today, but there's also a CLI, and you can do a lot of the kind of repo management type stuff and authentication management stuff that you do that you'll want to do with Arraylake right here in the CLI. So this is just an example of listing the repositories in this organization, and I could create more repositories, delete them, and so on. With that, I think Ryan has one more slide that he wants to share, so which I'm going to share, and then we'll take questions.
Yeah. So as Joe's putting that up, we're using today as a this showcase seminar as a chance to announce the official launching of what we call the private beta for Arraylake. So where we're going is to make Arraylake a service that's available to everyone, just like S3 is a service available to everyone. For now, so far we've been working with a few design partners on building out Arraylake, and it's deployed in production with those design partners. And we're really ready to have a few more early adopters join as partners to take Arraylake for a test drive. So if the features that we've described feel like they could be useful to you and your team, and you're interested in experimenting with something like this, reach out to us. I'll share a link in the chat about how you sign up for this. But at this point, we are opening up to the broader world of folks who are interested in playing around with this technology. So with that, we will wrap up our seminar, and we'd love to take some questions.
All right, thank you very much, Ryan and Joe. That was great. All right, so now we move into questions and comments. I'm going to stop the recording.